Hi everyone, this is the first in a series of 3 videos that I'm going to do on differential calculus, and this is intended for the International Baccalaureate course Maths Standard. So in this first video we're going to go through limits, the derivative function, simple rules of differentiation, the gradient of the tangent, and then finish off with the equation of the tangent and the normal. Now in mathematical terms, the limit is the value that a function approaches but cannot exceed. And it's similar to a brick wall or a ceiling. So the idea is that the function gets closer, but never touches the limit and never can get beyond it. Suppose we want to investigate the limit of this series, 1 plus a half plus a quarter. There's a rather famous mathematical joke, and it goes like this. An infinite number of mathematicians walk into a bar. The first one orders a beer, the second one orders half a beer, the third one orders a quarter of a beer. The barman says you're all idiots and pours 2 beers. And it's exactly this idea of limits. So here it is here, 1 beer plus a half a beer plus a quarter of a beer plus ... So the idea is that if we manage to get all the way to infinity and add this all up, then we would be pouring 2 beers. That's the limit of it. Let's have a look at how it works. We're going to do the sum of a geometric series here. Do you remember this formula? So this is a geometric series. We're multiplying by a common ratio each time, by half. So here's our first term, multiplied by 1, take away a half to the power of n, divided by 1, take away a half. I've done 0.5 just so I can fit it on the page. Tidying up the denominator is 0.5, and then I'm going to bring this denominator up the top. This is 1 divided by 0.5. So how many halves go into 1? 2. So here's just a simplified expression for the sum of n terms of this series. Now if we want to take the limit as n approaches infinity, this is how we write it. So I've got lim, and then underneath my condition, n approaches infinity of this expression here. And what that means is I want to figure out what this value is as n gets incredibly large. Okay, I'm going to turn it back to my half now because that's going to be important. Same expression. And here I'm going to do 1 to the power of n, which is just 1, divided by 2 to the power of n, like that. Okay, what happens when I substitute infinity into here? What do you imagine is 2 to the power of infinity? It is infinity. And what is 1 divided by infinity? That's actually equal to 0. So infinity is so big it doesn't go into any number, doesn't divide into any number at all. So 1 divided by infinity is 0. That'll beg the question as to what infinity divided by infinity is, and you can go and explore that one for yourself, but we only need this one in order to solve this problem. So 1 divided infinity is 0. So that is 0. So that means it's equal to 2 multiplied by 1, take away 0, which is 2. And then we've actually proven that that sum of that series, 1 plus a half plus a quarter, is actually equal to 2. Okay, and that's how we do it. So let's look at another one. Here's the limit as x approaches infinity of 3x squared minus 2x plus 1, all divided by x squared minus 5x. So we could substitute the infinity in, and essentially we would end up with infinity divided by infinity, which doesn't help us at all. So we've got a different way of solving these sorts of questions. We're going to take the highest power of x out as a common factor of both the denominator and the numerator. Okay, it's a bit scary looking. Alright, so essentially what I've done, taken x squared out the front. If I expand that all out, this is what I'm going to get. Have a look. X squared times 3, 3x squared. Minus 2x squared divide x is 2x. Plus 1 on x squared times x squared is 1. And on the denominator, x squared times 1 is x squared times negative 5 on x is negative 5x. Alright, these two cancel out. And I'm left with this expression here. Now, can you see how all these x's are on the denominator? That means 2 divided by infinity and 1 divided by infinity squared and 5 divided by infinity. What are they? They're all equal to 0. So 0, 0, 0. Can you see what the limit is? 3 over 1, which is 3. Now, big question for you. What do you suppose graphically that means? Think about where the x-axis is. As x tends to infinity, the limit is 3. That's an asymptote. It's actually the horizontal asymptote. So basically, if I was drawing this graph, this will be a terrible picture, I apologize. I would have some sort of asymptote happening here. Not really sure from this whether it's coming up from below or down from above. We'd have to do a bit more investigation. But that's actually what this is. It's an asymptote. Okay, now this one's slightly different. This time we want the limit as x approaches 2. So I've got x squared minus 4 on top and then x minus 2 on the bottom. Can you see the issue? If I substitute the 2 in, I get 2 minus 2, which is 0 on the denominator. And we can never divide by 0, even when the numerator is 0, which it is in this case. So 0 on the denominator is a no-no. We've got to do something in order to get rid of that denominator. So what we're going to do is factorize the top. Now we know that x squared minus 4 is the difference of 2 squares, so it's going to become x minus 2, x plus 2, and these two cancel out. As soon as I can cancel out that denominator, I'm going to be fine. So I'm going to be left with the limit as x approaches 2 of x plus 2. And now I'm fine to substitute in that 2. So putting the 2 in is going to give me 4. You might have noticed that as soon as we do the substitution, we no longer need this notation. Okay, but up until then, you have to keep it. Now this is what the graph looks like if you're interested. So this is actually a straight line. The straight line y equals x plus 2, but it's got a hole in it at that point. So it doesn't exist at the point 2, 4. Okay, we're going to move on and have a look at what differentiation is and what calculus is. And we're going to start by revising gradient. So recall that we can calculate the gradient of a line through 2 points. Here I've got the point A and B by using this formula. M is equal to y2 minus y1 and x2 minus x1. So for the picture, if I would substitute in 4 take away 1 on the numerator and 2 take away 1 on the denominator, and it gives me a gradient of 3. How do we find the gradient of the tangent when there's only 1 point? I mean, we can't use the gradient formula. We can't do 1 take away 1 divide 1 take away 1. It would give us 0 divide 0 and it's undefined. Well, we could draw a triangle and use rise over run. Or we could make a table and start with a point here, work out the gradient and creep it closer and closer and closer and closer and try and guess the limit. Or we could use calculus. So let's choose 2 points. Here's the first one, x and f of x. So that's the y coordinate. And then I'm going to put another point up here and I'm going to call it x plus h. So it's x plus a little bit. And its corresponding y value is going to be f of x plus h. So I hope you're comfortable here with my notation. H is meant to be a small number. I've drawn it quite big on the graph so you can see it. The gradient of the line between these points, we can just use the gradient formula for because we've got 2 points. So it's going to be f of x plus h take f of x divided by x plus h take away x. And just tidying up the denominator, I get this. To find the gradient of the tangent, we calculate what's called the derivative, okay? And this is the formula here. So we can see this bit, we just worked that out on the previous slide. That was the gradient of the secant between these 2 points. This is saying squish these 2 points together, slide this point down, make h tend towards 0 until it sits on top of here. Find the limit of that gradient when h is 0. Okay, so this first bit is the limit as h tends towards 0, and this part here is the gradient between the points. Okay, and that, in its essence, is what calculus is. The derivative is called the gradient function. Now this is really important. That's why I've put it in big, bold yellow letters. we've always got to come back to what does it actually mean. When we find the derivative, we are finding the gradient of a tangent at a particular point. Now let's just look at a bit of notation. When we find the derivative, we say we are differentiating y with respect to x, and that means we're finding out how much y changes as x changes. There's a couple of different ways we can write it. We can write y dashed or f dashed of x or dy dx. Now this last one here comes from this notation here. This funny little squiggle here is a lowercase delta in the Greek alphabet, and it means a very small change in y and x. So it's kind of like the gradient formula, little change in y divided by a little change in x. All right, let's have a look at how we do this from first principles. We are going to learn a shortcut, but we have to know how to do this using this formula as well. This formula is given for you on your formula sheet. So there's our derivative, and can you see how I've put the notation in? F dashed of x. Okay, so it's the limit as h approaches 0 of f of x plus h minus f of x divide h. What's this mean? This means substitute x plus h in wherever there's an x. Okay, it's going to look a bit ugly. Here's my x squared minus 3x plus 5. So that's that bit. Take away f of x. I need to put it in brackets because I'm taking away the whole thing, divided by h. Now we're going to expand that all out. So this is x squared plus 2 times h times x plus h squared, which is all there, minus 3x minus 3h plus 5. Take the negative through the brackets. Minus x squared plus 3x minus 5. All right, always when you're doing these sorts of questions, several things will cancel out. Our x squareds cancel out, our 3x's and our 5's. All right, let's rewrite it with what's left. Now you should get to this point now where our h can cancel through here, and it can. Can you see how there's an h in every single term? All right, so we're going to cancel that. Okay, so let's cancel. So just have a look what we did there. 2x h divide h is 2x. H squared divide h is h. Minus 3h divide h is minus 3. Okay, we've got rid of that denominator where the 0 was going to cause us an issue. We can now put the 0 in. So that's going to give us 2x minus 3. Okay, so we're at the point now where we have done our first derivative. This is what it means. This is the gradient of all of the tangents to this curve. If we want to know the gradient at a particular point, all we would do is substitute it in here. We'll get to that a little bit later. Okay, but this is the gradient of all of the tangents to this particular curve. Let's have a look at some common derivatives. So if I went through that process for all of these, I would end up with this. So for x squared, the derivative is 2x. For y is equal to x cubed, the derivative is 3x squared. For y is equal to x to the fourth, the derivative is 4x cubed. For x to the fifth, it's 5x to the fourth. You're starting to see the pattern? For x to the sixth, it's 6x to the 5. So here's the pattern. For y is equal to x to the n, the derivative is nx to the n minus 1. So basically, any power function, you're going to bring the power down, and then multiply by x, and then drop this power by 1, always. So if I had x to the 7, it would be 7x to the 6th would be the derivative. There are some simple rules of differentiation. Here's the first one. If we have a coefficient of x, it's going to be multiplied by the power when it comes down the front. So we just kind of include it. So this 3 will come down and multiply by the 6. So it's going to become 18x squared. Have a look what I've done here with this notation. Because I didn't have a y equals or an f of x equals, I kind of just made my own thing up. This still means find the derivative of 6x cubed with respect to x. It's kind of taken the place of the y. So that's another way you can write it if you want to. So d dx of 6x cubed is 18x squared. So 3 comes down, multiplies by the 6 gives us 18, and we drop the 3 by 1. We differentiate term by term. So suppose we've got 3 different terms. Okay, we're just going to do this one minus this one plus this one. This says find the derivative if f of x is equal to this. All right, let's have a go. 5 times 3 is 15. X to the power of 4 minus 3 2's are 6, x squared plus, bring the 2 down, 2 6's are 12, x to the power of 1. Okay, there's our derivative. The derivative of ax is a. So if we want to find the derivative of y is equal to 6x, for instance, it's going to be 6. Let's have a look at y. So here it is, y is equal to 6x. That's actually 6x to the power of 1. Bring your 1 down, and then that power is going to go to 0. What's anything to the power of 0? 1. Okay, so anytime you've got a coefficient in front of just an x to the power of 1 term, it's just going to become the coefficient. And then finally, the derivative of a constant term is 0. So let's differentiate y is equal to 3. Now I'm going to show you how to do this. By the time you've practiced this a bit, it will become second nature. So I'll show you why it is, and then you can probably forget about it and just think anytime you see a number, it's just going to go to 0. So here it is, y is equal to 3. I'm going to manufacture an x term. So here's x to the naught, because x to the naught is 1. So this is true. Would you agree? All right, the 0 comes down and wipes everything out. This would go to -1, but it doesn't matter. Okay, so as soon as the 0 comes down here, 3 times 0, gone. Okay? So let's have a go at finding the derivative of this. Y is equal to 3x to the power of 5 plus 2x minus 17. Okay, so we're going to go 5 3's are 15, x to the 4 plus 2. That's it. So that one I think you probably do understand at this point. This here is that one where we've got a coefficient in front of an x to the power of 1 term, and this is an x to the naught term, so the 0 comes down and wipes it out. Let's try another one. Okay, so I've got minus 3x to the 4th plus a quarter x. That's okay. All right, so the 4 comes down, gives me minus 12x cubed plus a quarter. So you can see how this is the x to the power of 1 term, like this one. So we're just left with the coefficient. Let's have a look what happens to y is equal to x to the 4th. So here's our first derivative, it becomes 4x cubed. Now there is such a thing as a second derivative, so I'll do it again. So 3 comes down, 3 4's are 12x squared. We could find a third derivative, bring the 2 down, 2 12's are 24x. A fourth derivative would be 24, and the fifth derivative would be 0. So when you start with positive powers like this, they eventually, if you differentiate them enough, they all end up at 0. Okay, a couple more things to look at. What about negative powers? We can differentiate negative powers using the same method. So find the derivative of y is equal to x to the -3. The -3 comes down, and then we drop this by 1. Now, that becomes -4, not -2. Okay? -3 minus 1 is -4. So there's our answer. In this case, because I got the x on the bottom, I'm actually going to have to put it into index form first. So that's 4x to the -1. Now differentiate, bring your -1 down, so -4x to the -2. Okay, so there's a couple of examples of negative powers. Did you notice anything? These powers are increasing in a negative direction. They're never going to end up at 0. So the positive powers that I did before, will go 4, 3, 2, 1, 0 if you kept differentiating them. In this case, if you kept differentiating, you'd end up at -infinity eventually. Fractional indices are fine as well. Have a look at this one. Differentiate f of x is equal to 2x to the 3rd. So our third is going to come down, x, and then I'm going to drop this by 1. So 1/3 take away 1 is negative 2/3. So 2 times 1/3 x to the negative 2/3, which is 2/3 of x to the negative 2/3. Of course, it could be written in this form, so we need to change it to index form first. This is x to the half. Now be careful here. A number of people will stop at this point and think that they're finished, and actually you haven't done any differentiation at all. All you've done is changed from square root into index form. So make sure you keep going and actually differentiate. So our half comes down, x, and I drop this by 1. Half take away 1 is negative half. Now we tend to write our answer in the form of the question. So this was in square root form. So we're going to put this back into that form. This means 1 over the square root of x. So there's the answer. Probably would get this right in the test if you left it like this. You need to ask your teacher. What about expressions inside brackets? Well, what we're going to do is expand them first and then do term by term. So I'm just going to do FOIL on this. I'm going to do x times 3x squared minus 7x minus 6x squared plus 14. Now differentiate. 3 3s are 9, x squared minus 7 minus 12x plus 0. There it is. Now we will be learning a method that's called the product rule in the next video, and this will actually help us differentiate products that are in brackets. What about quotients? This one's okay. We can split this into two fractions because it's top heavy, like this. All right, it's going to become 3x on 4x, which is just 3/4, minus x squared on 4x, which is x on 4. Okay, now let's go and differentiate this. So f dashed of x, that's going to be 0. It's got no x. And this is negative 1/4, so the derivative is just negative 1/4. So when we've got top-heavy fractions like this, we can split them into two separate terms and differentiate term by term. Now with a quotient like this, we actually can't do anything because it's bottom-heavy. We can't split this up into two separate fractions. But we will be learning a method called the quotient rule in the next video, which will help us differentiate quotients. Okay, we're finished with looking at the rules and how to differentiate. I just want to return back to what does it actually mean. The derivative finds the instantaneous rate at which some quantity is changing in relation to another changing quantity. Now so far we've only looked at the gradient of a tangent at a particular point, but there are other applications. Now differentiation is not only restricted to y and x. There are many other physical quantities that we can find the derivative of. A really common one is to differentiate something with respect to time, and we'll meet that in a couple of the other videos. But here's an interesting one. Do you recognize this formula? It's the volume of a sphere. Now we can find the derivative of this. We can find dV dr. Now I just want to point out something here. At this stage in our mathematical journey, we can only differentiate with respect to one variable. So we couldn't have, x and y here, or r and t, for instance. It wouldn't work. But pi is not a variable, it's a constant. It's a number. So this is going to be fine. We're going to do dV dr. So we're going to find the derivative of v with respect to r. Let's have a look what we've got. The 3 comes down, multiplied by pi r squared. Okay, toning that up, we get this. Now, do you recognize that formula? This is the surface area. Let's have a think about this. When we differentiate volume, we get surface area. Now, why on earth would that be? So let's just have a think about this and see if we can make sense of it. Here's a volume of a sphere. So it's changing somehow. The volume is changing. So say it's been inflated like a balloon, and the radius is changing. How much is the volume changing as the radius changes? That's what differentiation is, remember. So suppose it's getting bigger. Suppose it gets just a tiny, tiny, tiny bit bigger. Would you agree it'd be like putting an extra coat of paint on the outside of the sphere, which is the surface area? Can you see how that might work? So here's an example. And this is from a field called kinematics. We're going to do a whole video on this, so don't worry too much about this at this stage. But consider a particle moving along a line where x of t describes the position of the particle at time t. So it sort of is like this, moving along like this. Okay, and x of t describes its position. Now, if we looked at the first derivative, that would be how much is the position changing as time changes, and that's just the velocity. Okay, so our first derivative would be the velocity of the particle. We can talk about a second derivative. So if I did the derivative of velocity, it would mean how much is the velocity changing as time changes, and that's the acceleration. Okay, more on that later. In this case, going back to our dy dx, it means how much is y changing as x is changing at the instant when x is equal to 1. That's what that means. Okay, so let's try and tie all this together. Find the gradient of the tangent to the curve f of x equals 3x cubed minus 9x at the point 1, negative 6. So we're going to find our derivative. We're going to do f dashed of x. So it's going to be 9x squared minus 9. Now this is the gradient of all of the tangents to that curve. We want the one that occurs at x equals 1, so we're going to substitute that in. See how I've put the 1 in here, and I've kept the dash, so I substitute it in, and I get 0. Okay, what does that mean? The gradient of the tangent to f of x at 1, negative 6 is 0. It's flat, horizontal, like this. In other words, at that particular instance, y isn't changing at all. So the logical next step is to find the equation of the tangent to the curve. And we're going to do this by using coordinate geometry methods. So here's the question. Find the equation of the tangent to the curve f of x equals 4x squared plus 2x minus 9 at x equals negative 1. We're going to start this question exactly the same way we did the last one by finding the derivative. So f dashed of x is going to be 8x plus 2. Substitute in negative 1 because this is the point at which we want the tangent. So substitute the negative 1 in there, and that's going to give us negative 6. So that's the gradient of the tangent at x equals negative 1. Now when we go to substitute into the formula, we can substitute in for m and x1, but we hit a bit of a roadblock at y1 because we don't know the y coordinate of this point. All we have to do though is substitute this into the curve. Remember this is y. So substitute our negative 1 in here will give us the y coordinate. Don't forget to put this in brackets because it's a negative. So this is going to be 4 minus 2 minus 9 equals minus 7. Substitute in, tidy it up. See how I've taken this plus 7 over the other side, and we get y equals negative 6x minus 13, which is the equation of the tangent. Now the graphics display calculator won't calculate the derivative, but it will find the derivative at a particular point, and it'll show the equation of the tangent, which is kind of nice. The first thing we've got to do is make sure the derivative is on, and this is probably the first thing you'll do after your calculator is put into exam mode, is you'll go into setup and make sure the derivative is on. So you go into any of the menu items like run or graph, and then you hit shift to setup, and you navigate down until you find derivative, and then you turn it on. Okay? Here's the previous question. Find the equation of the tangent to the curve f of x equals 4x squared plus 2x minus 9 at x equals negative 1. Firstly, we're going to go to graph and enter the function. Then we're going to go F6 and draw. Then we're going to hit F4 for sketch and F2 for tangent. You can see that here. Now we've got to tell it where we want the tangent. We want it at negative 1, so you just type negative 1 in like this. And then the gradient of the tangent at negative 1 appears, which is here. There's our gradient. And also the y coordinate. Now if we want to find the equation of the tangent on the calculator, then after we've hit F4 for sketch and F2 for tangent and entered negative 1, we hit XE twice. The first time displays the derivative, The second time displays the equation of the tangent, and here it is here. Okay, last little bit for this video. The normal is perpendicular to the tangent at a particular point. So it's a new word to learn. So here we've got our tangent coming up here, touches at only one position. The line that's perpendicular to that is called the normal. So we could be asked to find the equation of the tangent or the equation of the normal to a curve. So to find the equation of the normal at a particular point, we start exactly the same way by finding the derivative. So y dash will be negative 4x to the negative 2 plus 6. Locate the point, x is equal to 1, and substitute it in. At x equals 1, y dashed is equal to negative 4 plus 6 equals 2. But this is the gradient of the tangent, not the normal. The normal is perpendicular to the tangent. Do you remember how to find a perpendicular gradient? We take the negative reciprocal. So flip it upside down, change the sign. Okay, we're ready. Here's our gradient, here's our point, substitute them into the formula. Now with these sorts of ones, when they've got a fractional gradient like this, I tend to take this denominator over here and go into general form, but that's just a personal preference. You don't have to. You could take the 10 over the other side and go into gradient intercept form. So 2 comes over, it's 2y minus 20 equals negative x plus 1. Like that. And then all I've got to do is take the x to the side where it's positive, which is over here. So tidying it up, here's the equation of the normal. X plus 2y minus 21 equals 0. Okay, last thing to do is to enter this in to the graphics calculator. So we type in y equals 4x to the negative 1 plus 6x into the graph part of the calculator and hit F6 for draw. Guess what? No graph appears. So it's just a blank screen. And that's because our viewing window is set too narrow. Quickest way to solve this is to hit F2 for zoom and F5 for auto. And there we have a graph. Now let's get back to what we were trying to do, which is find the equation of the normal. So we're going to hit F4 for sketch and this time F3 for normal. And we've got to tell it where we want it, and that was at x equals 1. So we type 1, then xy, xy, and here is our equation of our normal. You will notice that the calculator always puts it in gradient intercept form, and that's okay. We did it before in general form, but they are equivalent. Okay, that brings us to the end of the first video on differential calculus.